Hello, and welcome to Lecture 11 on the topic of Faraday's and Lenz's laws. This continues our discussion of combining magnetism with electricity and builds on ideas from lectures 9 and 10. Okay, so let's talk about Faraday's law, Lenz's law, and motional EMF, which is a special case of Faraday's law. Let's look at our objectives. Our first objective, we want to understand that Faraday's law states that magnetic fields can induce a current, but only if the flux of that field through a circuit is changing as a function of time. So we need a changing magnetic field to induce a current. A constant magnetic field does not induce a current. We want to understand that Lenz's law clarifies the direction of the induced current from a changing magnetic field. Very much Lenz's law is a continuation of the ideas of the right-hand rule that we've been discussing. And we want to learn the case of motional EMF as a simple case of Faraday's and Lenz's law. Okay, so let's get to it and define Faraday's law. All right, well, it is the third big and final big law of electromagnetism. The other two were Gauss's law and Ampere's law. Okay, so together, these three laws tell us how electricity and magnetism are united. Okay, so what does it actually tell us? Well, Faraday's law states that a changing magnetic field can induce a voltage across a conductor, okay? And usually applied to current loops where the magnetic field flux through the loop is a quantity that changes over time, okay? Now we'll define magnetic field flux in an equation in just a moment under our key equations. But what it is it's simply the amount of field that passes through an area. So think a area in kind of three dimensions like this, and this is your magnetic field. And if it's perpendicular to the area here, and the area is A, then your flux is just field times area. It's just the product of field and area, okay? But the point is, if that flux changes, then a current is induced because an EMF is induced. Now, in practicality, there's a number of ways that we'll actually see that magnetic flux change, and those would be kind of quantified in this way, all right? We could have the B field strength just simply change because maybe it's an electromagnet and we're just turning it up or down. We could have the loop area change because that would change the amount of field that fits inside the loop. We can have the angle change because if it's not 90 degrees, then there's not maximum flux. You could have an area that is exactly lined up with the field, in which case there's zero flux, even though there's a field there, right? And number four, you can have the loop moves through a non-uniform magnetic field. So that's effectively the field strength changing, but it looks a bit different because your loop is actually moving through that field, okay? Now, an interesting thing is that Faraday's law only gives us the magnitude of the induced EMF, which means we need Lenz's law for the direction, okay? So it combines, Lenz's law does, with Faraday's law to give the direction of induced EMF. It states that the induced EMF and resulting current produces a new magnetic field that opposes the change. It's a very useful way of thinking about it, in the flux of the original magnetic field. Okay? Now I say that opposes the change is a useful way of thinking about it, but you need to get some practice so you understand what that means. Let's look at a simple example, okay? And we'll test your understanding with some questions coming up. So here are two very basic Lenz law examples. Okay, zoom in a bit on this. So imagine we have a magnetic field in both the upper and lower figure that points into the page. In the upper case, the magnetic field is increasing in strength. So that is like case one, that's just a B field that's getting stronger. B field, of course, is being shorthand for magnetic field, okay? Well, the magnetic field is getting stronger and we need to oppose that change. Then we're going to have an induced current that wants to produce a magnetic field out of the page. And indeed, if you curl your fingers of your right hand in the direction of the arrow shown, in the counterclockwise direction, what direction does your thumb point? Away from the page, away from the screen. That's telling you that the induced current produces a magnetic field that is out of the page, thus opposing the gradual increase, or quick increase for that matter, of the magnetic field into the page. It opposes the change, okay? Well, what if the magnetic field pointing into the page again is decreasing? Well, now the induced current is going to try to recreate what was lost, because again, it's going to oppose the change, and so it's going to try to bring back the original field strength, so to speak, right? And that's just a useful way to think about it. So again, if I curl my fingers on my right hand in the clockwise direction, my thumb must point towards the screen or into the screen, and thus that tells me that my induced current is trying to oppose the decrease by recreating the lost field strength pointing into the page, okay? All right, now what are eddy currents? Well, eddy currents are a case of EMF. We're not going to do any problems with eddy currents because there's no way to quantify them, but they are an interesting concept. It applies to the induced EMF and currents in a solid rather than a wire. Okay? As a conducting solid, like a plate of metal, passes through a magnetic field, chaotic currents, okay, that's why we can't quantify them because they're going to move in complex ways, are formed along closed loops in the solid. So, I mean, the solid doesn't have one clear path for the current to take, but the current will naturally take many different paths. Well, it's hard to imagine, so let's look at a picture. Okay? So here we have a big conducting solid, a slab of metal, and we're moving it through a magnetic field, which is effectively like case 4 of moving a loop, but in this case, the loops are just being formed inside the solid, but moving it through a non-uniform B field because we go from no B field over here to uniform for a while and then no field again, which effectively means we're changing the exposure to the B field. But as this moves through the B field, through the magnetic field, this slab of metal, here are the induced loops. Okay, current is induced along those loops. Now that produces a force that opposes the motion. Okay, so there's a magnetic force exerted on the conducting slab here that opposes the motion. Shown here, the induced eddy currents mean that the conducting solid experiences a force that would slow the conductor. Okay, all right, let's get to our key equations. All right, so we have magnetic flux, Faraday's law, motional EMF. Okay, first one. Magnetic flux. It's a new variable. It's represented by the uppercase letter phi, okay? Subscript B here for magnetic. All right, it is quantified in the units Weber, which is represented as uppercase WB, and Webers are just Teslas times square meters, okay? So it's magnetic field strength times area, all right? And we can indeed see in the definition of magnetic flux, it's field strength times area. Specifically, it's the component of the magnetic field that is perpendicular to the plane of area. Or it is, well, here's the area, or it's the B times A multiplied by cosine of the angle between the magnetic field vector and the normal vector, which is the way we usually define the area. We define it by its normal vector. What this looks like as a picture is the following, all right? So this is our enclosed area, a circle, okay? And we have some magnetic field here that is not exactly perpendicular to the area, which means that there's an angle, theta, a non-zero angle, between the normal vector of the area, which is by definition perpendicular to the area, and the magnetic field, okay? So the flux then we would calculate by B times A times cosine of theta, okay? So you can see that flux is maximum when the magnetic field is exactly perpendicular to the area, because in that case, you have cosine of 0, okay? So that's the definition of magnetic flux. Let's move on to Faraday's law, all right? So this is what it looks like in equation form. And what does it tell us? Well, it tells us that the induced EMF measured in volts is equal to, well, this difference multiplied by the number of wire loops in a coil. Because sometimes you might have more than one loop, and so in that case, the strength just goes up linearly, so we can have N here for the number of loops. But the real interesting part is this part here inside of the absolute value. And what this represents is the rate of flux change, all right? Because of course, flux is up here, right? And it's being divided by a change in time. So it's flux per time, change in flux per time. And it's the absolute value of change in flux per time because the flux might be decreasing or increasing, but the EMF will always have the same magnitude. We don't care about whether the flux is going up or down. We just care that it's changing because that will tell us the induced EMF. So you can see if you change a magnetic field very quickly, you get a big EMF. If you change it a lot, then you get a big EMF, right? So that's how you can get a lot of current out of magnetic field. It's either changing it very fast or with large magnitude, okay? And last up is motional EMF right here, okay? So motional EMF is both this picture and this equation. I included the picture just to kind of make sense of what it is. Motional EMF is all about a conductor that is part of a circuit, usually, that then is moving, right? So the motional part is because the conductor has a certain velocity. It's moving through a magnetic field, okay? All right. So in that case, the variables in the equation, L is the length of the conductor, okay? So this would be L as in the figure. V is the velocity, and specifically it's the velocity perpendicular to the magnetic field. In some cases, they may not be perpendicular, so you'd have to take a component of the velocity, but they usually are, okay, the velocity there, okay? And then, if we want to, say, find the current, we'd simply use Ohm's law to relate the induced EMF from the motional EMF equation to the resistance in the circuit in order to find the current through the circuit. And the circuit, of course, passes through the conductor, then through the resistor, something like that, okay? All right, so let's take a look at our practice problems. We got two types, problems that involve using Faraday's law and Lenz's law to relate the change of magnetic flux through a closed loop to the induced EMF and current in that loop, okay? And then type 2, well, motional EMF problems, okay? And the motional EMF problems are interesting because they may involve the conducting rod as part of a complete circuit and the induction of current. In fact, they usually do, all right? And they also may involve forces, which you'll see is quite interesting. Okay, so let's do some concept questions. Now, I would always recommend you try these first. So let's read them, pause if you need to, try to answer it, and then I'll briefly talk about the solution. Question 1. An adjustable square loop of wire lies in the plane of the page. A constant magnetic field is directed into the page. As the square loop is reduced in size, the induced current in the loop is in what direction? Okay, so this is the picture. You got a loop. At first it's large, and then it's reduced in size. Okay, so what's going on then? The magnetic flux is definitely decreasing because now there's less of the field can fit inside the loop. The field hasn't changed. So what direction would the induced current be in? Okay, make sure you have an answer. Okay, so we know that we need a direction of current in order to get some field back. We need to strengthen the field into the page because we lost some, right? Lenz's law tells us the induced current always opposes the change. So we need to get some field back inside the loop, which means we need, this is the B induced. In other words, this is the magnetic field that's being created by the induced current that itself was created by the change in the magnetic field, or at least the magnetic flux, right? Because of course the field didn't change here, but the flux did. Okay, I know that's a mouthful. This is the magnetic field created by the induced current that was created itself by the change in the flux. Okay, but here's the direction. Okay, of course, by the right-hand rule, we know that since I already showed you the direction of the induced magnetic field, you simply curl your fingers of your right hand, in this case the clockwise direction, and get your thumb to point into the screen. So indeed, clockwise is our induced current direction. Okay, the induced current opposes the decreased flux out of the page. Okay, all right. Well, I should say into the page, but you get the idea. Okay, because it said, yeah, yep, that should just say in. Okay, into. All right, let's do another one. Question 2. A long straight wire is in the plane of a rectangular conducting loop. The straight wire carries a constant current, I, as shown. While the wire is being moved towards the rectangle, the current in the rectangle is in what direction? So this would be an example of a current carrying loop moving through a non-uniform magnetic field. Of course, in this case, it's the wire that's moving and the loop is at rest, but that's all relative velocity. Okay, so here's the magnetic field created by a current carrying wire. Okay, refer to lecture 10 for that, right? You can find that direction with the right hand rule, your thumb pointing in the direction of the current and your fingers curling in the direction of the magnetic field. Now we're going to move that wire in this direction. That's the velocity of the wire towards the current carrying loop. That's going to induce a current in the counterclockwise direction. Why is that? Well, the counterclockwise induced current is because we want to oppose the increasing flux into the page. Okay? Notice that the B field produced by the induced current points out of the page. See, it points in the opposite direction, opposite the original B field. Here, the induced current pointed in the same direction as the original field. That's because there was a decrease. But here, since there's an increase due to the closer proximity of the wire and thus getting closer to the stronger parts of the field, whenever there's an increase, the induced magnetic field points in the opposite direction. In both cases, they oppose change, but there's definitely like either the directions are the same if there's a decrease, or the directions are opposite if there's an increase. Okay? All right, let's do it one more time. I think this is a real good one. A bar magnet is falling through a loop of wire with constant velocity. The south pole enters first, and the loop is in the plane of the page. As the magnet enters the wire, the induced current, as viewed from above, is in what direction? Okay, so give this one a try. Pause if you need to. Okay, all right, so here it is. This is the falling into the loop. I have a side view and a top view. Okay, from a side view, we can see the south pole falling in. We know all the magnetic field lines point towards the south pole. Okay, which means from the top, we would have magnetic field lines that look like this, all coming out of the page. Okay, all right. And yep. And so then we have, while entering, the field is out of the page and increasing. Okay. Yep. So, oh, I forgot to change the notation here. This should be out of. So the wording is correct, but the notation should show the little dots. That's why I paused there for just a second ago. because these ones should have little dots on them to show that they're coming out of the page as correctly shown in this figure. Okay, so but here let's read this statement. The statement is correct. While entering, the field is out of the page and increasing. Thus, the current I, the induced current, tries to prevent the outward field with clockwise current. Okay, so the clockwise current goes. You turn your fingers. See, now that's pointing into the page, right? So it's opposite the current direction of the magnetic field. It's opposing the increase. Okay, good. Okay, now what about the case, part B? As the magnet exits the wire, right, the induced current as viewed from above is in what direction? Okay, so now it's fallen all the way through the wire, and now we got it like this. Okay, so give that one a try. Let me show you my picture. Okay, so now it's fallen, the bar magnet has fallen all the way through. Okay, now the field lines point in this direction. Okay, so they're all pointing out of the page again. Okay, and so then we can see that while leaving, the field is out of the page again, right? All the field lines are pointing out of the page and decreasing in magnitude. Okay, so again, these should be dots. I'll fix this. Okay, fix it, but these should be dots, not x's, because they represent vectors that are pointing out of the page. So you're looking at the tip of the vector, not the tail. Okay, but while leaving, the field is out of the page and decreasing. Thus, the current I tries to recreate, okay, the outward field, and we get a counterclockwise direction. So curl your fingers here in this direction, curl your fingers that way, your thumb points out of the page, because indeed it's trying to recreate this field that is being lost as the bar magnet falls lower and lower and moves further and further away. Okay, all right, good. So that's the directionality. Definitely take some practice, something you got to work with. Let's do some of the computation problems, which are not terribly difficult, pretty straightforward calculations here. Example 1. A uniform 888 millitesla magnetic field passes at an angle of 20 degrees to the normal of the plane of a wire loop of 0.32 square meters in area. If the field is steadily increased to 1.33 teslas over a period of 11.5 seconds, then what is the induced EMF during that period of time? I just had the wrong word here. It should say EMF. Okay, so I went ahead and just calculated the magnetic flux in both cases. You don't need to do this as a separate step, but since this is the first time we're doing it. All right, so magnetic flux is the initial magnetic field times area, which is unchanged, times cosine of the angle. The angle doesn't change, but you do need to take the angle into account. Okay, so we go ahead and do that. And then we go ahead and find the final magnetic field with the new increased magnetic field strength, but still same angle. And so we end up with 0.26 Webers initially and 0.4 Webers as our final magnetic flux. So therefore, our induced EMF, according to Faraday's law, and there's only a single loop, is just equal to the absolute value of the change in flux over the change in time, which then would just be 0.4 Webers minus 0.26 Webers divided by 11.5. And all I did here to do the absolute value is just put the larger one in front. And so they would end up with 1.6 times 10 to the negative 2 volts. That's how much induced EMF there is, measured in volts. Excellent. Okay, let's do another one. A loop consisting of 7 turns of wire is oriented perpendicular to the magnetic field. Okay, so if it's perpendicular, then theta is going to be 90 degrees. Okay, or rather, theta is going to be 0 degrees because of the way it's defined. So in that case, we won't need the cosine term. So part A, if the magnetic flux through the loop decreases uniformly in magnitude from 2.41 Webers to 1.16 Webers in a time of 8 milliseconds, and the induced current is 820 milliamps, then what must be the resistance? Okay, so this one we are going to consider wire. We do have a full loop in this case. So let's consider what's going on. So from Faraday's law, we have this expression. Okay, and here we have Ohm's law. So then we can then solve for the resistance from Ohm's law, and then insert our expression from Faraday's law to find that the resistance is going to be 1 over the current times n, the number of loops, times the absolute value of the change in flux over the change in time. So 7 loops, an induced current of 0.82 amps. There's our change in flux, and there's the time it took to change. And that tells us that our resistance has to be 1,330 ohms. Okay? Because any other resistance would have created a different current. So the current set the resistance. Okay? All right. Okay, so, or the resistance set the current, I should say. All right, and then part B is just a quick follow-up to work with the flux term here. So the area enclosed is known to be 200 cubic centimeters. Then what is the final magnetic field strength? Okay, so we can just go here and then just solve for B. Okay, because we were never given the field strength, but once we're given the area, we certainly have enough information to solve for it. So our final flux was 1.16 Webers because it did decrease. And we'll just divide by the cross-sectional area. Make sure to convert 200 cubic centimeters to 200 cubic, or just converted to cubic meters, that is, and there is 10 to the negative 4 cubic centimeters or cubic meters in a cubic centimeter. In other words, there's 10,000 cubic centimeters per cubic meter. Okay, so excellent. And there we go, 58 Teslas. All right, looks good. Let's do our last concept question. All right, so this is a fun one. A square loop of wire moves with a constant speed, v, from a field-free region into a region of constant uniform magnetic field, as shown. Which of the 5 graphs correctly shown in induced current, or correctly shows the induced current in the loop as a function of time? So it not only does it move into the field, it moves back out of it. Okay, so this loop is going to move into the field. Okay, so it'll be in the field, still moving at constant velocity, and then it's going to move out of the field. So we need the graph that matches that phenomenon. Think about which one it could be. Well, which one would represent the induced current in the loop as it moves into the field, through the field, out of the field, and then continues on its way? All right, got an answer? Well, it's got to be C, okay? C matches the behavior. Why is that? Well, because we have a constant induced current due to the constant rate of change when it enters the field, okay? And it's going to be in one direction. Then there'll be no induced current as it moves through the field, because if it's moving through the field at constant velocity, there's no change in flux, right? So for a while, you have no current. But then when it leaves the field, there's going to be an opposite direction due to Lenz's law, an opposite current. But again, constant, just goes from 0 to constant, stays constant for the whole time it's leaving, and then drops back down to 0, because once it's out of the field, well, obviously no more induced EMF, no more induced current, okay? Now, if it was accelerating, then obviously these would not be constant lines, but since it's constant velocity, it's flat like this, like a step function, okay? All right, let's do another computational problem. So, example 3, last one in our type 1 problem. If a field reverses its direction in 1.06 seconds while maintaining a magnitude of 0.105 Teslas, what is the magnitude of the average induced EMF in a single circular loop with a radius of 5.65 centimeters? Okay, it's a pretty straightforward question. I'm just gonna combine ideas here to use Faraday's law, and by combining ideas, I'm just not gonna separately solve for the change in flux. Instead, I just wrote the numerator as so, and then I plug in my values, right? So I have, if it's going from one direction to another, I'm gonna end up with negative 0.105 Teslas minus 0.105 Teslas. So essentially, this is just 2 times the magnetic field, all right? And then times pi r squared divided by the change in time, the elapsed time. And there we go, 1.99 millivolts. Okay, let's do a motional EMF problem. Okay, so a conducting rod of length 12.6 centimeters is moving with a constant velocity through a uniform and constant magnetic field of 24.9 milliteslas, as shown. What is the motional EMF that develops across the rod? All right, and then what is the electric field strength inside the rod? Okay, so to find the motional EMF, it is very much plug and chug, because we know everything. We know field strength, we know length, we know velocity. So we just put in those values, and there we go. We get 0.255 volts. Excellent, okay? And again, this is just the equation and the key equations for motional EMF. Now, what about to find the field strength? Well, you just got to remember the relationship between EMF, which of course is voltage, and field. And by definition, the electric field is just volts divided by length. All right, volts per length. So here it would be the overall length of the rod, because that would give you the electric field within the rod. All right, so 0.255 volts divided by the entire length of the rod, and there you go, 2.02 volts per meter. But if you think about it, dividing by the length is the same as saying that electric field is just magnetic field times velocity, which indeed it is. So you can also express the electric field inside a motional EMF conducting rod like this as just magnetic field times velocity. And of course, you get the same answer. Okay? All right, good simple one to get started. Let's do another one. So, an airplane with a wingspan of 59 meters flies parallel to the Earth's surface at a point where the downward component of Earth's magnetic field is 0.49 times 10 to the negative 4 Teslas. If the induced potential between the wingtips is 41.3 millivolts, what is the plane's speed? All right, so this is a way to determine speed based on the actual electromagnetic behavior. Okay, so here's our plane flying along, right, perpendicular velocity to field direction. Okay, excellent. So we're going to use our motional EMF equation. And there we have our velocity, which we're going to solve for. We're just going to isolate that. Okay, we know all the other variables, so it's simply a matter of plugging them in and getting a velocity. A rather slow airplane. Maybe this is some sort of glider. Okay, all right, so that one was very much similar to the previous one, other than that it had an application because we had to think of it as an airplane. Okay, example 6. Okay, now we have motion EMF where we're going to talk about a current, because now rather than just building up a voltage across a rod, now we have a rod that's connected into a complete circuit. Thus, a current can flow through due to the EMF that's induced in the rod. So, a long vertical wire carries a steady 70 amp current. Okay, as shown in the figure, a pair of horizontal rails are 2 meters apart, and a 20 ohm resistor connects points A and B at the end of the rails. A bar is in contact with the rails and is moved by an external force with a constant horizontal velocity of 0.9 meters per second to the right as shown. The bar and the rails have negligible resistance. At the instant that the bar is shown, it is 0.2 meters from the wire. What are the induced current in the resistor and its direction through the resistor? Okay, so it'll be direction through the resistor. Does it go this way or does it go that way? Okay, all right. And by the way, we're not going to use this length for this problem. We only care about the distance of the conducting rod or bar from the wire. Okay, so what are our steps here? So one thing is to use the right-hand rule as described in lecture 10 to think about where the magnetic field goes from, or where it's created from the current carrying wire. So hold your thumb in the direction of the wire and then curl your fingers so you can tell that the magnetic field over on the right-hand side where our bar is located is going into the page. Okay, now we need to find its strength with this equation, again, from lecture 10. Okay, so let's go ahead and find the magnetic field strength at this point, right at this point where the bar is located. Okay, so we have our permeability constant times the current in the wire, and then times, or all divided by 2 pi times the distance between the wire and the bar. And we get 7 times 10 to the negative 5 Tesla. So, weak field, which makes sense because it's not a very large current. Okay, or maybe I should say you need really, really large currents to get reasonably sized magnetic fields. Okay, so now we're ready to take that information and plug it into our motional EMF equation. Okay, so then we can find the induced EMF in the bar by taking the field strength times the length of the bar times the velocity of the bar, because we know all that. We know that the bar has a length of 20 centimeters, and we know that it's moving at a constant velocity of 90 centimeters per second. Okay, so we plug in those values, and we find out that the induced EMF in the moving bar is 1.26 times 10 to the negative 5 volts. Excellent. Okay, so what were we asked, though? We were asked for the current. Okay, well, all we need for that is Ohm's law. Okay, so then we just say, okay, well, we've got the EMF. We were told the resistance, shown here in the figure, 20 ohms, so we can easily find the current. And it turns out that the current through the circuit is very tiny, 6.3 times 10 to the negative 7 amps. You need a very sensitive multimeter, okay? And as far as the direction, from the right-hand rule in Lenz's law, the current is clockwise from A to B, okay? So why is that? Well, think about it. We have a magnetic field going into the board, but we're getting less and less of it, right? So we're decreasing the area that's enclosed by the loop. As the area decreases, then the induced current has to flow to try to recreate that decrease, which means it's going to flow in the clockwise direction from A to B. Okay? All right. So let's do one that involves a force. The next two will involve forces. And notice the previous one said there was some external force that was maintaining that constant velocity. Well, that begs the question, can you find that external force? Yes, you can. Okay, so example 7. A conducting rod whose length is 1.6 meters is placed on a frictionless U-shaped metal rails and that are connected to a light bulb. All right, the light bulb has a resistance of 4 ohms. So the 4 ohms would be right over here. All right, the rails and the rod are in the plane of the page. A constant uniform magnetic field of strength 2.2 Teslas is applied perpendicular to and out of the paper. Right, so these are the vectors that all point out of the paper. They're the tip of the vectors. Okay. What is the magnitude of the external applied force needed to move the rod to the right with a constant speed of 6 meters per second? So anytime you have one of these motional EMF problems that involve a complete loop like this, there's always a required force to maintain constant velocity. Because since it doesn't matter if you're moving in this direction or you're moving in this direction, in both cases, there's going to be a magnetic force that opposes the movement. So to maintain velocity, you have to have an external force. So here are our forces, okay, to maintain a constant velocity. Well, if we have two forces to maintain a constant velocity, that is none other than dynamic equilibrium, right? It means our sum of forces in what we could call the x direction sum to 0. In other words, it means that the external force equals the magnetic force. So we are asked for what's the magnitude of the external applied force. That means in order to find it, we just need to find the magnetic force, the force that's acting on this conducting rod. Okay, so how do we find that? Well, the magnetic force on the wire is found with the formula that we saw first in lecture 9, the magnetic force on a current carrying wire. All right, it's just BIL. Excellent. Okay, so that's because certainly there is a current flowing through this this rod, all right, there's obviously a magnetic field, a constant one, and the rod has some length. So the magnetic force on this rod is magnetic field strength, which is uniform, constant, right, times current times length of the rod. But what's the current? Well, we now know how to find the current because the current we can find through the motional EMF formula, all right? The current is the induced current from motional EMF, okay? So it's the current that comes from this formula right here, okay? Now, obviously, this formula gives us EMF, not current, but we can relate it to current using Ohm's law, like we did in the previous example, okay? So here we have Ohm's law, and that, which has allowed me to rewrite the motional EMF equation to solve for I, okay? So that's all I've done here is combine Ohm's law with the motional EMF equation to solve for the induced current. And what am I going to do with that induced current? Yep, I'm going to plug it in to the force on the rod, okay? So now my magnetic force on the rod is the magnetic field times the current, but now the current is this whole thing in parentheses because it's the induced current, and then times the length. So this is so interesting because this means that the magnetic field is both producing a current in the rod and then exerting a force on the current it produced. Quite remarkable, isn't it? Okay? And so that means that the magnetic field force would be, if we combine our B's, we have a B squared and an L squared, because we have an L here and L here. And our magnetic field force is obviously equal to our external force. So that means our external force is this. Now, this is a very useful equation, right? Because this actually is the expression that you'd use anytime you want to find the force to maintain a constant velocity for a motional EMF problem. Okay, so this is a very useful equation. Okay, so in this case, we can just plug in our values. We plug in our field strength, we plug in our length of our rod, we plug in our maintained constant velocity, and finally our known resistance. And we find that the force to keep this rod moving at a constant velocity of 6 meters per second is 8.9 newtons. Okay, if we applied any less force, it would slow down, it would accelerate, right? Gradually coming to a stop and then going back the other way, right? Or, if we applied more force, then it would be, if the external force is bigger than the magnetic force, it would pick up speed as it went. Okay, so let's do it one more time with gravity. Okay, so example 8, last example of the lecture. A length of zero resistance wire is constructed into a long vertical U shape, and a conducting bar with a resistance of 1.16 ohms and a length of 1.33 meters and a mass of 148 grams is allowed to slide vertically down the sides of the U-shaped wire. Okay? A horizontal magnetic field of 437 milliteslas is maintained. What is the terminal velocity of this conducting rod as it slides down? Okay, let's look at the picture. Okay, so here's the idea. This is all vertical. So here we have our conducting rod that has a resistance and a mass. We never determined the mass before because we neither had an acceleration nor gravity in the previous example. But now there's an external force, but now our external force is the gravitational force, okay? And there's still the magnetic force that is determined exactly like in the previous example, okay? So what's the setup then, okay? So again, we're going to have dynamic equilibrium. Why? Well, because we were asked for the terminal velocity. Well, the terminal velocity is once there's a balance between the gravitational force and the magnetic force, once it picks up enough speed, okay? Now, we're not worried about the process of it getting there. That's beyond the scope of this class, but we can certainly solve for the state when it is in dynamic equilibrium, okay? All right, so we have a balancing of the gravitational force and the magnetic force. They're equal to each other. So that means, in other words, that the gravitational force mg is just equal to the force external as we determined in the previous example. Notice F sub t represents terminal velocity. So then simply I solve for the terminal velocity, plug in my values, and there we go, 4.98 meters per second. Okay, all right, well, I hope this lecture has been interesting and informative. Thank you so much for watching.